Everyone, my name is Ashley, and today I'll be going over question 1, bits from the CSM 61B midterm 2 review. So the first part of bits asks us to write a function that determines whether an integer is a multiple of 4 using only a mask and equality operator. So just go over what those are. Mask is an and symbol. It's an and operator, and equality operators are the equal to and the not equal to. So those are the only two things we can work. Only 3 things essentially we can work with. So let's go over what exactly makes an integer a multiple of 4. So 4 in binary is represented like this, and when it's a multiple of 4, multiples of 4s are adding this added to plus 0 added times some number. So basically, we're just adding this multiple times, adding this itself like times some number essentially. So starting from 0, the first time we add 4 to become 4 would be this, and then we add it to become 8. It would become this number, 12, this number. And so this is how we can see what multiples of 4 look like. One thing we should notice is that zeros, there are 2 zeros in the least significant bits for all multiples of 4. And we can, this checks out because when you add 4, you're only impacting the bit, the 2 to the second bit and onwards. You're never, since the 4-bit has zeros in both the least significant bits, never altered the least significant bits here. And this is a property unique to multiples of 4, because in order for both of these to be 0, either the number has to be 0 itself, or it has to, or the smallest possible digit is a 4, which makes it a multiple of 4. So let's try to create a check that checks if the least significant bits of a number are 0 using the AND. So one thing we learned about AND is that when you AND a number with 1, it essentially returns that number. So if you AND 0 with 1, it will be 0, and 1 with 1, it will be 1. So we can use this information to AND the last 2 bits essentially with a 1. So we do 1, 1, and then we can use that information to compare to what we want. So we know we want to and 1, 1 is equal to 3. So we want to AND this bit string with 3. So what this will do is regardless of number, it'll turn everything before the last 2 digits into 0, and then it'll have some number for the last 2 digits. If it was a multiple of 4, both of these would be 0, so this would turn 0. Elsewise, if it was a multiple, it'll have some ones in at least one of these bits, and that will translate to the final number. So we know if it's a multiple of 4, the least 2 significant after ANDing with 3, the whole number should essentially turn into 0. So the least 2 would turn into 0s. So we just check if this number is equal to 0. So it returns if 0 is equal to x and 3, and that is our how we implement this check. So the next question is asking us whether integer is odd using only bit shifting and equality checks. So bit shifting includes left shift, which appends zeros to the right or least significant digit of the number. A right shift, which just cuts off the right right of the number essentially, or the least significant bit of the number. And then we have arithmetic right shift, which that also cuts off the last bit of number, but it maintains the sign. So one thing we know that we can determine quickly is that since we're in binary, the 2 options that we have 0, 1 for bits. And then and if a least significant bit of a number is 0, then we know it's even. If it's 1, it's odd. Because that just means it has an additional 1. You're adding additional 1 to a bunch of multiples of 2, which are even. So using this knowledge, we want to write some kind of program that will check if what the least significant bit of it is. If the least significant bit of it is 1. So let's try. One way we could try to do this with bit shifting is we could try to right shift a bit. So bit by 1, so it cuts off whatever is in the least significant bit. So this wouldn't matter, and then we can left shift it back by 1 again, and then so that would append 0 to the least significant bit. And with that knowledge, we can compare it to the original. We could compare that to the original number we got and see if it's the same. If it was odd, it would not be the same because this would have used to be a 1. If it was even, it would have been the same because we're replacing a 0 with 0. Let's quickly go over an example of this. So, for example, if we're going with this bit string and we want to determine whether this is odd, first thing we could do is we can right shift it. So this essentially would get rid of this value, move everything to the right, and add a 0 to the front. And then we would left shift it, and then we would left shift this new number. So basically, we're moving everything to the left and adding 0 to the rightmost digit. And this is not equal to the original one we had originally. So that's how we would know if it was odd or not. So let's translate this to code. So first thing we want to do x. We want to right shift it by 1. So we do x right shift 1, and then we want to take this number and then we want to left shift it by 1. Do left shift by 1. And then after we have this new number, we want to compare it to what we had originally. So we compare it with x, and we check if it's not equal to. And that's how you determine what our integer is on, using only bit shifting and quality checks. So moving on to part 3, we want to rotate a 32-bit integer left by k bits. So k is less than 32. Okay, so I guess one way I like to approach problems like this is to break into smaller examples. So let's pretend we're rotating a 4-bit integer, and then let's see how that would work, and then we get 5 there. So pretend this is our 4-bit integer, and then it's 4 bits, and our pretend k is equal to 1. So we shift everything to the left by 1. It essentially look like this. Like all these will go to the left, and this one will go to the very right. That's what's going to the very right. So one thing we should notice is that we're rotating the integer, and we're breaking into 2 groups. We have this group and this group, and which each group follows a different behavior, but every bit inside the group follows the same behavior. So in this group, we're essentially shifting it, moving every element left by 1, or in by 1, because k is 1 in this case. So that's one thing. So that's one thing we should notice. So just moving to the left by 1, and then on this one, this is moving to the very. This essentially is moving to the very leftmost. So the kth element from the very kth most significant element is moving to the left. So these are 2 operations we want to implement. I think that the easier one we could implement is the first one, where we shift everything to the left by k, because there's an operation for that, left shift. So we just write x left shift k. So in this example, it would have looked like this, and then we have k1. So we have this number, but that's not quite the final result we want here. We want to move this to the end, or we want to replace this 0 that we just added with this the most significant digit. So one way we could do this replacement is using arithmetic shift, or like arithmetic right shift. So the thing is, we saw we only had to move everything to the k forwards. So in this one, we're shifting it right essentially. And the thing is, in this case, we're shifting it right by 3. And 3 is 4 minus 1, which is the length of the bit string minus k. So we would also want to implement that as well. So we do x right shift, and then we would have, and then the bit length of integers we're using is 32, and we'll do 32 minus k. And so this would basically remove all the 32 minus k least significant digits until we get this, which is this and beyond, which is all the digits we still want. So now we have 2 halves, which in this case would be doing 4 minus 1, so 3, so it'd be this, that'd be 1, and a bunch of zeros for it. So now we have 2 halves of the number that we want, essentially. And one way we could do it, we can fix this is by ORing it. So one way we would want to we could combine these strings or do OR. So we add an OR statement here, and then by combining these two, we would get the designated integer that we wanted. So going into the fourth part, we want to write an expression that swaps the bits at bit positions A, along with bit position B, and within one given integer n. And we're noting that the least significant bit is the bit position 0. So there's 2 parts to this swapping bit problem. So obviously one of them is swap bits. But before we want to blindly swap the bits, one thing that will save us time is if we check if the bits are actually different. So if both A and B are the same value, then there's no point in actually swapping them because it would have no actual impact on the number. So by implementing a check if the bits are same, then essentially we can save us time by not actually doing the swap. So first thing we want to do is check how if the bits are the same. So one thing we could do is we can use the and one principle we learned before and try anding the specific bit we want with 1 in order to get it, and isolating it using the left and right shift, and then we can compare if they're the same. So the first thing we want to do is, in order to get the starting with the bit position A, we want to essentially compare that position with the bit in that position with 1. So in order to get a 1 to the 8th position, we need to left shift it by A. So the first thing we want to do is, if we have an if statement, we want to left shift by A. And then after we left shift by A, we have number 1 with a bunch of zeros after it. And then we don't care about any of the other bits. We only care if the 8th bit is 1 or not. So then we just add this new value with n. And this would, since everything else is 0, everything will turn to 0 except for potentially 8th bit, the 8th bit would just turn into 0, whatever originally is 0 or 1. After we have that value, we can right shift it by A, so we get rid of all the unnecessary zeros after it, and this would just isolate the bit to itself. So I guess we can try visualizing it here. So we're given the string again, and we want to get the first bit, or A is equal to 1. We want to get the first bit. So first thing we'll do, we create a new bit string where we add is left shift by A, which is 1. We'd and these together. Everything will turn into zeros except 8th bit. And we get rid of with right shift by getting rid of the 8th bit. And then now we're left with the bit we want. So we can see that this works, and we can repeat the process with bit B. So we have one left shifted by B, and it with N, and then right shifted back to by B. These are our two values. And the thing is, we want to check if they're the same. Or like we want to execute code if they're not the same. So we just add a not equals to in between these two, and then in our if statement track. So now we checked if the bits are not the same. Now we know they're not the same. Now we want to swap them. So one thing we learned about is in order to toggle a bit, we can use XOR, or specifically XOR with 1. So like if we did 0 XOR with 1, that would turn into a 1. And if we do 1 XOR with 1, that would turn into 0. So basically, this will turn the bit into its opposite, which is exactly what we want, because we know that since they're different and there's only 2 options, it has to be the other one. So we can set we will alter n by setting n equal to by XORing with 1, and we want to left shift it to the 8th position in order to XOR the right bit. And then we do the same thing with B. So we do n XOR 1, and then left shift by B. And then so after these two operations, n should be what we want, and then we would have exit this for loop, and then we would do return n. And this should give us the expression we want. And for the last part, they ask us to write an expression equivalent to x times 35 without using multiply, divide, and then percent. It's blanking. This is blanking on me. But yeah, basically without any arithmetic operators. One thing we can use in bit operations, or one thing we should specifically keep in mind, is that left shifting and right shifting is essentially a form of multiplying. So the best way to visualize this, like if we just had number 1 and we left shifted by 0, and this is essentially multiplied by 2 to the first. And you see that would have been correct. It went from 1 to 2. And then now, if we add another 0, we're essentially multiplying by 2 to 2. So it's like 2 to the number of zeros. And then this values to 4, which is 4 times 1, and so on. So the best way we can write an expression equivalent to this is by breaking it down into breaking 35 down into its into binary, and then using left shift in order to combine it. So let's convert 35 to binary. So 32 is the smallest power of 2 that is less than 35. So we do 1 there. It's 2 to the 5th, I believe. And then 2 to the 4th is 16. So we do 35 minus 32. That's 3. 16. 16 is greater than 3, so we put 0 there. Then we do 2, 3. That's 8. 8 does not go to 3, so we put 0 there. We do 2 to 2, which is 4. There's no way 4 can fit into 3, so that's not true. Then 2 to 2, which is 1. There's 1, 2. And so we subtract that, and there's 1, and then 1. So this is what 35 looks like in binary. And we can implement this through left shifts. So by left shifting each power, essentially like left shifting each power for each bit that's 1 in 35. So the most significant bit that's 1 in 35 is 2 to the 5th. So this would be equivalent to left shift by 5. So we could do x left shift by 5, and this would be equivalent to like this is essentially equal to, well, doing x times 32. And then so we can add that in. So we do x, left shift 5. And then so we have x is 32, but we still need to shift it by 3 more. So essentially we can do a left shift. We can add it to a left shift of x to the 1 because that, or like x to the 2, my bad. Because we want to multiply it by 2. And we want to shift it by there should be a left shift by 1, I believe. And we'd add in a left, there's a left by 0, so we'd add in 0. X, which is essentially no left shift. So let's walk through this on an example here. So like for multiplying 1 by 35, we first shift it by 5. So this would be equal to 32. And then we'd shift it by, add it with a shift by 1, which is equal to 2. And then we have itself, which is 1. And then if we add this all together, we would get 35, essentially, in binary. So that's how you would write an expression that would multiply without actually using arithmetic operators. Hopefully this walkthrough helped. And good luck on the midterm. See you guys next time.